Hey guys, welcome back. This is the second half of the study guide for the midterm for physics. So we're going to get into Newton's laws and some more kinematics. All right, so a launch yards drop from a tall building. If there is no air resistance, after 4 seconds, the speed of the ball would be. Our acceleration is negative 10 meters per second squared. So that tells me that my velocity is going to change by 10 meters per second every second. After 1 second, it would be going negative 10. After 2, it would be going negative 20. After 3, negative 30. And after 4, negative 40. But they're asking for speed, which is a scalar, so the magnitude would only be 40 meters per second. A ball thrown horizontally at 10 meters per second from a 50-meter cliff would hit the ground in how long? I need to make two charts. I need to have a y direction chart and an x direction chart. For a horizontal launch, our initial velocity in the y direction is always 0. If we're on Earth, our acceleration is always negative 10. And they're telling us that the cliff is 50 meters. So the displacement from the top of the cliff to the bottom of the cliff would be negative 50. In the x direction, there is no acceleration, so my starting velocity and final velocity will be the same. And so I'm going to use my y direction to find time and plug it into the x direction to get the horizontal displacement. All right, so to get the time, I'm going to look at x minus x naught equals v naught t plus 1/2 at squared. In the y direction, our initial velocity is 0. That cancels out. And I'm going to solve for t. I'm going to multiply 2, divide by a, and square root. And I'm going to have 2 times negative 50 over negative 10. And again, you want to be careful of the sign because your calculator will not like it if you try to take a square root of a negative number. So 2 times negative 50 would be negative 100. Negative 100 divided by negative 10 would be 10, and the square root of 10 is 3.16. This is the only thing that has to be the same in both of our charts. So then if I look at the x direction, the acceleration cancels out, and I just have v naught times t. So this is going to be 10 meters per second times 3.16 is 31.6 meters. All right, calculate the maximum height of a projectile that is launched at an angle of 30 degrees with respect to the x-axis with an initial velocity of 60 meters per second from level ground. So in 2 dimensions, if it's not horizontal launch, we have to take our initial velocity and separate it. Separate it into what's going on in the y direction and what's going on in the x direction, because those things have different things affecting. So I'm going to start with a vector that is going to represent this velocity. We're saying that this is 60 meters per second. This is 30 degrees. This is going to be v x naught. This is going to be v y naught. So our initial velocity in the x direction, our initial velocity in the y direction. And I'm going to use sine and cosine. So you want to make sure that your calculator is in degrees. I know that based on which math you are, it could be in radians. So I'm going to use cosine to get v naught x. I'm going to say that cosine of 30 is going to be equal to v naught x over 60. So v naught x is going to be 60 cosine 30, which I think is 48, but I'm going to check with the calculator. Nope, I was wrong, 52. So good thing that I actually checked. And then the y component, I'm going to use sine for. I know that sine of 30 is going to be v naught y over 60. So V naught y is going to be 60 sine of 30. I know sine of 30 is 1/2. So V naught y is going to be 30. All right, so to get my maximum height, I only have to worry about the y direction. Time of flight and maximum height are only y direction problems. So my V naught is going to be 30. When it gets to the highest point, it's going to be 0. So there's going to be a moment where the y velocity, as it decreases, as it switches position, it's going to pass through 0 momentarily. That's the highest point. This is going to be -10. So it's going to take 3 seconds for this to happen, but I'll use the v squared equation to figure out how high this is. So v squared equals v naught squared plus 2a x minus x naught. I'm going to take v squared minus v naught squared. I'm going to divide by 2a. I'm going to have 0 squared minus 30 meters per second squared all over 2 times -10. So 30 squared is 900 divided by 20 is going to give me a maximum height of 45. And then this is 3 seconds, right? Because every second it's going to change by 10 meters per second. So how far it goes sideways, well, this is only half of the flight. There's going to be a whole additional half of the flight as it's coming down, back down to the ground. So for this chart, I'm going to use my 52 meters per second, and that's my beginning and end in the x direction, and my acceleration is 0. And now I'm going to double my time. And then I'm going to use my x minus x naught equation. And I'll give you guys all the equations. That cancels out. And I'm going to have 52 times 6, which should be 312, or pretty close to what that is. A ball is thrown straight up in the air. At its peak, its speed could be best described as 0. So in order to go from a positive to a negative, you have to pass through 0 if you think about a number line. So it's going to be a moment where it's passing through 0 before it comes back down. The whole time, it has an acceleration of -10. It's feeling gravity the whole time, even at that moment when it's 0, because it comes back down. If gravity was 0 there, when you throw it up, it would just stay there. That doesn't make a lot of sense. All right, equilibrium versus non-equilibrium. Equilibrium means that constant velocity, which is constant speed and constant direction, or not moving at all. Non-equilibrium would be something that's going faster or slower, or turning, or both. So a truck traveling straight down a hill at 15 is equilibrium. Bob at rest in his chair is equilibrium. A lemon falling from a tree would be acceleration. They want me to put an N. So non-equilibrium, a lime at rest in a tree would be equilibrium. A piece of paper falling at terminal velocity is also equilibrium. So it's moving, but it's not speeding up or slowing down or changing its direction. The direction's down the whole time. A calculated rest on a table would be equilibrium, but the Earth in orbit would be non-equilibrium, because even if you are saying that its speed isn't changing, the direction is changing because it's in an elliptical path, a nearly circular path. The same thing with a satellite going around Uranus. A Segway going straight down a road at a constant speed is equilibrium. And a go-kart going a constant speed of 3 around a curve would be acceleration because its direction's changing. All right, Newton's first law. A 10 kilogram block is at rest on a flat surface. What's the normal force? So this is where we started. These two arrows are balanced because it's at rest. So the normal would be equal to the weight. To go from mass to weight, we multiply by 10. A 20 Newton block is being pulled at a constant speed sideways by a 10 Newton force, see below. So it's directed above that. Determine the normal force, determine the frictional force. So my free body diagram would have friction going back, normal also going up, and weight going down. I need to break this into components because this force that's at an angle is both pulling up and pulling to the side. So this would be Tx, this would be Ty. I would use cosine to get Tx. So I would say that cosine of 60 would be equal to Tx over 2. So Tx is going to be 2 cosine 60, or 1. And then for Ty, I would use sine, and I would say that sine of 60 is Ty over 2. So Ty is 2 sine of 60, which is going to be 0.866 times 2, which is 1.73. All right, in the y direction, we're balanced. And we're going to take the forces up minus down. In this case, there's two things up. Normal's up and Ty is up. When you pull like this, you're pulling up a little bit. Part of it, you're lifting it up. The normal doesn't have to be as much. So this is going to be Ty plus n minus mg is equal to 0. So I'm going to add mg to the other side and subtract Ty. So n is going to be equal to mg minus Ty, which is going to be 20 newtons divided by 1.73 newtons, which is going to be 18.3 if I round this down to 1.7. In the x direction, it's also f net equals 0 because it's a constant speed. We're out of space, right? So you would just take the forces to the right minus to the left. That's going to be Tx minus f. And then to get friction, coefficient of friction from this, we know that mu, the coefficient of friction, is the ratio of the force of friction divided by the normal. How hard is it to drag something compared to how hard it would be to lift it up? So in this case, our friction is 1, and our normal is 18.3. So this is 0.055. No units on mu. It's only less than or equal to if it's static. In this sense, this is sliding, this is kinetic, so it's always going to be that. The following 5 Newton block is at rest on an incline. Determine the frictional force on the block that's keeping it at rest. Mg, F, N. The rule with these is that we rotate them. Our angle is always the angle with the horizontal. When I rotate this, mg is at an angle, and the 30 degrees, this upper angle, is the same as the lower angle. And I go over this in another YouTube video where I demonstrate why this is so with geometry. Which is actually the name of a television show for Julius Center Miller in the 50s. Why is it so? All right, so the component that's balancing friction is this guy down here, which is mg sine of 30. So down the incline, I would say F net equals 0. So this is going to be mg sine of 30 minus F is equal to 0. So mg sine of 30 is equal to F. And mg is 5. Sine of 30 is 1/2. So my force of friction is 2.5. All right, a 10 kilogram sign below is hung by 2 wires. Determine the tension in the wire directed at an angle. So T2 is like this, T1 is like this, mg is like that. Remember, wires, beams can only direct forces in their direction, which we call axially. So I know that I want to break this into components. I'm going to draw it off to the side like a good physics student. And I don't know anything really about the x direction. So I'm going to look at T2y because I do know something about the y direction, mainly mg. All right, so I'm going to use sine of 60 is going to be equal to T2y over T2. So T2y is going to be T2 sine of 60. So T2y is not real. So if I can express it in terms of T2, which I actually want to solve for, that's beneficial to me. And then in the y direction, I'm going to say F net equals 0. I'm going to take the forces up minus down. This is going to be T2 sine of 60 minus mg is equal to 0. I'm going to add mg to the other side and divide by sine of 60. So this is going to be 10 kilograms times 10 meters per second divided by the sine of 60, which is going to give me 115. Second law. So this is when we have unbalanced forces, and since it's linear, this is going to be things speeding up, slowing down. A ball is dropped in the absence of air friction. Its acceleration after 5 seconds is going to be negative 10. So the acceleration is always g, it doesn't change. A block is at rest on a frictionless surface. It experiences a horizontal force of 4 newtons pulling on it. What is its acceleration? So here is my diagram. If I look at this, I can see that my acceleration is going to be in the x direction. That's where it's unbalanced. And so I'm going to say F net equals ma in the x direction. So that's going to be T equals ma. So A is going to be equal to T over M. My tension is 4 and my mass is 2. And so my acceleration is 2 meters per second per second. What is acceleration? Acceleration is the change in velocity over time. What 2 parts make up velocity? Speed and direction. Ball is under 4 forces. One is pulling it 20 newtons east. One is pulling it 15 newtons north. One is pulling it 25 west. One is pulling it 10 south. what's the resultant? So I have to combine the ones in the direction. In my east to west direction, I'm going to have 25 minus 20, which is going to give me 5 newtons west. In my north and south directions, I'm going to have 15 newtons minus 10, which is going to give me 5 newtons north. When I combine these, I have to do it in the head to tail method, and I have an arrow that I can get the length of by taking the square root of the two sides. So 5 squared is 25, 5 squared is 25, 25 plus 25 is 50, the square root of 50 is 7.07. And they say that they want the vector, so I would call this northwest. We're saying that this is north, this is south, this is east, this is west. All right, circular motion. Tina experiences 25 meters per second of centripetal acceleration during his train for a trip to Cedar Point. How many G's would that be? To go from acceleration to G's, we just divide by 10. A car travels around a loop with a radius of 100 meters in 20 seconds. What's the car's centripetal acceleration? So we can get our velocity by doing 2 pi r over t. Our radius is 100. Our time is 20 seconds. So I'm going to have 2 times 100 will be 200 divided by 20 would be 10. I'm going to have a velocity of 10 pi. And then centripetal acceleration is v squared over r. So this is going to be 10 pi squared over r, which is going to end up giving me pi squared, right? Because 10 squared is 100, and 100 divided by 100 would be 1. So my centripetal acceleration is pi squared meters per second. It's close to 10. A car travels around a level loop with a radius of 150 meters in 25 seconds. If the car has a mass of 1,200 kilograms, what's the frictional force necessary to keep the car from slipping? So as the car goes, the frictional force is going to be our centripetal force and so I'm going to take 1,200. Oh, I got to get V, right? They give us this in terms of our radius and our time. So I'm going to have 300 pi divided by 25. Gives me 37.7, I'm going to say, meters per second. That's squared, and then our radius is 150. So I have 11,370 newtons is friction. In the y direction, our normal is just going to be equal to the weight, because that's F net equals 0. So that's going to be 1,200 times 10, which would just be 12,000. And then mu static is less than or equal to the force of friction over normal. So remember, if it's not slipping, friction's only as much as it has to be. And so my force of friction was 11,370. My normal was 12,000. So this is going to be 0.95. The mu must at least be that. And typically tires on like a rubber tire on a dry concrete road, that's about 1. So we're getting pretty close to what the limit would be. All right, the last one is that a man goes to a planet with triple the mass of Earth and half the radius. He weighs 1,000 newtons on Earth. What on the new planet he weighs? So the formula for this is GMM over R squared. So my universal constant's not going to change, so I'm going to put in a 1 for that. His mass isn't going to change, but we're saying that the mass of Earth is going from 1 to 3, and the radius is going from 1 to 1/2. So I'm going to have 3 divided by 1/2 squared, and that's going to give me a factor of 12. So if he weighed 1,000 newtons on Earth, his new weight would increase by 12 times. So he's going to be 12,000 times on the new planet. All right, guys, good luck on the midterm. If you have any questions, feel free to email me.